Our final energy term in molecular mechanics force fields is electrostatics. So for the electrostatic energy term, we have a sum over all the atoms from I equals 1 to n, where I is the atomic index, then sum from j equals I plus 1 to n, so we're summing over all atom pairs here, is the partial charge of atom I times the partial charge of atom j over 4 pi epsilon naught, the permittivity of free space, times Rij, the interatomic distance. So this is the classical charge-charge interaction from electrostatics that you've probably seen in a general physics class. So let's go over the parameters and variables here. So our parameters in this case are Qi, if I can draw a Q, Qi, and Q, for 2, Qj, which are our atomic partial charges, which are typically going to be specified in units of electrons. So if I specify those in terms of electrons, something with half an electron charge being 0.5, etc. And we have our variable, same as the variable from the van der Waals case, is Rij. Wow, we really can't draw the indices today. All right, Rij, which is the interatomic distance. Typically, again, in units of angstroms. So you'll notice that this is not necessarily going to give us kcals per mole here, because if it's convenient to express in terms of electrons and angstroms, that we're not getting all the cancellation depending on the unit here and the permittivity of free space. So typically what's done is you compute this in whatever unit you like, and then you convert at the end to back to kcals per mole or whatever main unit you're using. So the internal unit that it's often used in terms of there is sometimes called a computational energy unit, which is about 332 kcal per mole. Or the inverse of that. Can't remember at the moment, something like that. But just be aware of that caveat that these units need to be converted at the end to get your final energy unit. Okay, so different types of interactions we can have depending on the sign of these charges here. If they're both positive or if they're both negative, so whenever they're the same, you get a repulsive interaction. Like repels like. And when the charges are the opposite, then this times this is negative. The interaction is attractive. So opposites attract in that case. You get an attractive interaction. Okay, so if we imagine just the case of positive and negative, for these cases it's the same, but you flip the sign relative to the y-axis here. So for our molecular mechanics electrostatic term, we're going to start at the E equals 0 at R equals infinity, because 1 over infinity gives you a 0. And then as you bring the things in, you start developing an attractive force. The thing goes negative when your charges are opposite, and this 1 over Rij just keeps getting bigger and bigger as R gets smaller. The attraction gets bigger and bigger and bigger, and just goes all the way down to minus infinity at short range. Sometimes more advanced potentials have what's called screening, where you'll multiply this times something that makes it go back to 0 at short range, so it doesn't go down to infinity. But this term, left to its own devices, yes, would just prefer to go to negative infinity. It would prefer for the atoms to be right on top of each other. That doesn't happen because of the van der Waals terms between them. The van der Waals make sure you get enough repulsion between them, and that's positive r to the 12th. So r to the 12th beats the 1 over r there in terms of the speed which it goes to infinity. So that's why oppositely charged atoms don't end up fusing with each other, but left to their own devices without that van der Waals term, they would prefer to just be right on top of each other. Okay, so as I mentioned, that is a sum over all atom pairs. There are a few restrictions about what these values can possibly be. So if you think about summing over all of the atoms that you have there, so the total charge of your system is going to equal sum over all the atoms of their atomic charges there. So that's the total system charge. So our total system charge is constrained to be whatever the charge of our total system should be. So if we have a neutral molecule, like a water molecule, then the charges should sum to 0. So whatever the charge of the oxygen is, the charge of the hydrogens has to be minus 1/2 that. So for example, if the charge of the oxygen and water is minus 0.8, then each of the hydrogens need to be positive 0.4. So these charges, they do have the constraint that they can't be any value, that they need to sum up to whatever the total charge of your system should be. And also within individual molecular fragments, they should sum up to whatever that molecule charge should be. Okay, so the electrostatics term actually ends up being the most cost prohibitive, the most computationally expensive term in molecular mechanics. And it may not look that way because it looks like it's the simplest term. And in terms of the actual algebra, it is the simplest term. It's just some multiplications and divisions. There's no addition, there's no subtraction, there's no multiple parameters. It's just multiplying and dividing and summing them up. But the problem is over these pairs is in how many of them there are. So as I've been bringing up for the last couple videos, you have on the order of n bonded terms. So the number of bonded terms scales linearly with the number of atoms because you're limited in how many bonds you can have per atom. But the number of atom pairs is quadratic. There's order n squared non-bonded terms. So let's just show that right now. So the number of bonded terms we get here is n choose 2. In n atoms, how many different pairs can you have? This is equal to n factorial over 2 factorial times n minus 2 factorial. N factorial over n minus 2 factorial is n times n minus 1. 2 factorial is 2. So there are n times n minus 1 over 2, which as n becomes very large, n becomes approximately n minus 1. So there are approximately n squared over 2 non-bonded terms that we have to deal with. Now you might say, well, that's fine, but we have the same number of terms to deal with for van der Waals. Van der Waals is also a sum over all atom pairs. And you'd be correct, except for the following caveat, is that van der Waals more quickly decays with respect to distance. Remember that the van der Waals has one term that depends on 1 over r to the 12th, and that decays very quickly. But the slower decaying one depends on 1 over rij to the 6th. So 1 over rij to the 6th actually still decays pretty quickly. In fact, by the time you're about 20 angstroms away, they typically aren't interacting at all through the van der Waals force, through the van der Waals potential. Electrostatics, on the other hand, has a much slower decay away towards 0. Notice that when I put out these graphs, I intentionally made this decay take very long to go towards 0, even though there's no scale there, but just emphasizing the fact that it takes a long time for 1 over r to go to 0. So that term is proportional to 1 over rij to the 1st, which takes a lot longer to reach 0 than 1 over r to the 6th. So this means that electrostatics ends up being the rate-limiting step in molecular mechanics. You can't cut off this interaction with respect to distance. You actually have to include pretty much all of the atom pairs that are interacting for electrostatics, and most of the heavy lifting in molecular mechanics is figuring out how to quickly sum over all of these atom pairs for electrostatics when you get up to thousands, tens of thousands, hundreds of thousands, or even millions of atoms. Because at millions of atoms, a million squared is a trillion. So you could have a trillion of these interactions when you have a million atoms. And you need some way to efficiently deal with that. And there are lots of sophisticated algorithms to deal with those things. Lots of things called Ewald summations, particle mesh, all kinds of research has been developed into getting this term to be computed quicker, because you can't just ignore the long range things, because as you go out, the number of atoms with respect to R is going to go up quadratically, whereas this only decays linearly. So you actually need to compute all of them in some way in order to get this term to decay at long distance. So even though electrostatics is deceptively simple in its functional form, it's actually where a lot of the effort and a lot of the brain power goes into making molecular mechanics simulations much faster and much more computationally efficient.